Please join me in welcoming Professor Hauser. Professor.
Thank you. So today, I'd like to talk about some work that largely it's work with Jake Cook, who is right now out at NASA Langley in Virginia. And we'd like to play around a little bit with these TiltWing aircraft. So the idea is, in part, that there's a class of vehicles coming along that like to make use of distributed electric propulsion. And we can put these electric motors in many different places. So this, for example, is a new vehicle out at Langley called the LA-8 for Langley Aerodrome 8. Aerodrome is what Langley was calling his little aircraft at the time. So anyway, the idea in part is that by being able to tilt these guys, we can turn on more motors because they're electric motors. We can have vertical takeoff, and then we can transition to conventional flight and then turn a bunch of the propellers off so that we can have a more interesting cruise. And part of the idea is these are things that are intended for doing this urban air mobility, okay? And when we're tilting the whole thing, instead of the propeller pushing onto the wings like happens in the Osprey, where the propellers are aligned with the wings, so the thrust that we're producing will do different interesting things. Also, because the wings will then be in the slipstream, this will help to perhaps keep the air attached to the wings. And so we can operate in what would normally be more of a stalling kind of a situation. Now, bunches of these things have been built. In fact, like here we see the CL-84 depicted, which was in the mid 60s that the Canadian Armed Forces made use of. But it was very complex aircraft, and while it demonstrated what it wanted, it didn't go as fast as they wanted in terms of jets to be able to get somewhere. Wasn't quite as maneuverable as helicopters and everything. So while it was very successful, it didn't end up getting selected for operational duty. So anyway, now when doing these things, one of the biggest challenges is this notion of being able to do the transitions. So recently, NASA has built different things, and they've sort of demonstrated that some pilots could fly the things a little bit. I've also had some loss of aircraft in the process as well. So we're interested really in understanding something about these transition maneuvers. And to do that, we wanted to have a fairly simple system that we can work with to point out what the details are. We've been playing with some of these wing transition maneuvers for a while. One of the easier ways to do things was to just say, okay, let's put a very complex system in and try doing some trajectory optimization. And that turns out to be fairly hard. So instead, what we wanted to do is come up with the simplest thing where we could actually gain some insights. And in fact, Jake and I have actually discovered quite a lot in the last week or two. So thanks, Eric, for making us do a little bit of work for a change instead of skiing, as things would go. Okay, so what's the idea? The idea is that we want to figure out a way to capture the forces the forces on the wing when it's in the slipstream of a propeller. So the idea, it looks a little complicated here, but we're traveling horizontally to the left on this diagram. So we have a velocity v that's coming into there. We're at some regular angle of attack here relative to that v, but because we're producing a lot of wind while producing the thrust, that's going to actually, give us an induced velocity w that's going to come down this way, and the two things together will give us a slipstream velocity, which will give us a different kind of an angle of attack to work from in terms of the wind that the wing sees. So part of the idea here then is we're going to come up with some new lift coefficients and drag coefficients, moment coefficient, that's based on the slipstream dynamic pressure instead of the dynamic pressure in the far field. And then since we want to put all these things together, we're also going to have a thrust coefficient that will help us to see, it will be also based on the slipstream guy here. And so this guy, if we're just hovering, then there's the Q bar is equal to 0. So this coefficient will be 1 when there's 0 free stream velocity. Should get rid of that S. And when there's 0 thrust, then this coefficient will be equal to 0. Okay, so how do we come up with doing this? Well, the key is that here, because it's a simple model, we're going to take the thrust. It'll be just a regular disk here, and we'll use momentum theory to determine what the induced velocity is. And then that together will give us our slipstream velocity. We can define the angle of attack, obviously, from this picture. And then we'll have our slipstream dynamic pressure. So if we put those guys together, there will be some extra rotations and so forth and so on to get our overall lift and drag coefficients. And those lift and drag include the effects of the thrust. As we can see, the thrust guy here is getting rotated into the velocity frame. And same with the other guys. Okay, so it's not really that complicated. It just looks like that when we're playing around with these things. So originally it was Richard Kuhn in the 50s with, I guess, his helper or collaborator, John Draper, that worked on this kind of thing. So here we can see a wing that's vertical here. We've got a couple of propellers that are overlapping that are blowing the wing. And then he was able to produce this experimental data that we have here with the dashed lines. And in the report, there's a little bit of confusion because at least one of them, instead of having the propellers like this, he added a nacelle around the motor, which then started to interfere with some of these things. Okay, so these wings sweeps were done at different angles, and for some different values of this this thrust coefficient, and he wanted to hold the thrust on the from the propellers to be constant, and so that required varying the motor speed while doing this, and wanted to have a constant slipstream pressure as well when we were doing these different things. So this gives us a little bit of an idea. And for example, here, this blue curve is with the coefficient of thrust is equal to 0. So that's just the usual lift curve that the system would have if we didn't turn on the propellers. So we'd get those lift and drag curves. And so we wanted to take those guys and come up with something that we could play with reasonably well for our explorations. So this is what we did. These dotted lines here just have more to do with how we constructed it. So we saw that there was, the usual linear-ish lift portion of this versus angle of attack, we'd have some peakiness here of the lift curve. There'd be some kind of a stall behavior. And here we're just treating it to be very smooth and extended out to 90 degrees so that we can operate there, and we can actually even go a little bit beyond 90. These circles here are just where we joined together so we'd have a C2 approximation for our lift, for a drag after curves and so forth, that would allow us to use this in a model for doing things. Now here, I wanted to point out, it says the lift and drag were based on experimentally obtained wing-only data. So that wing-only data is, this blue one here, where we've turned off the propellers. And it turns out that, if you make use of him, then as you go to these higher ones, we do get things that are at least representative of what the data looks like. It's also, the wing only means without the nacelle, okay? And we extended it so that we can, fly the thing dropping in any of these different fashions. Okay, so how did we build something up here? What we've got is we're imagining that we have a flying wing. We'd like to have a fuselage in there, to produce a little bit of drag. Here we just kind of did something simple and just put a sphere there so that we would get some drag from the body and not doing things. So not have the complications of actually having to specify a full fuselage and et cetera. We want to do this having similar mass and geometry properties for this Langley Aerodrome number 8 forward wing. So we built up those things. Again, I mentioned we'd had a spherical body so that we would have some fuselage drag showing up, but none of the complications. And we're being really simple, all forces at the vehicle center of mass. The wing is fully immersed in the propeller slipstream, and we only wanted to work in the longitudinal plane. In fact, we restricted quite a bit more than that. And we pretend to have direct control over the wing tilt angle and over the propeller thrust, okay? Here we could just see some of these things that we have in terms of body drag and so forth. And since this work is sort of NASA-like, we're using the old things of feet squared, slugs, and so forth. So the overall mass of this guy is really more, the weight of it's like 32 pounds, giving a mass of about 14.5 kilograms. Since I asked Jake, what the heck is what is that for the number of slugs? Okay, so one of the important things when working with almost any system is to understand the equilibrium manifold, the set of trim conditions. So here we're working in a local level frame. So U bar is just our velocity going in the forward direction. W bar here is the vertical velocity, okay? We're gonna operate with the vertical velocity is equal to 0 pretty much. And our trim condition, as usual, is to ask that the accelerations be equal to 0. What we can do then is we're going to vary the thrust and the tilt angle. So this is the wing tilt angle, theta W, T is the thrust. We're going to vary those guys in order to achieve each desired situation here. So the W's, we're just going to fix that completely to 0, or always to 0. And the U bar is going to be our forward velocity that we see along the horizontal axis of these three curves here. And for the idea here, we've got our CL curve. Okay, so when we're at zero velocity, of course, our tilt angle is going to be up at 90 degrees. We're not moving, only the thrust is doing something. So at that point, we're going to be down here at zero angle of attack. We're going to, need, in principle, the most thrust that we can do. Now, as we start to move along, then we're going to be at different velocities. And we see somewhere around 18 here, where we've got, a turning point of our tilt angle that's showing up. And that guy corresponds with hitting this maximum lift, maximum point on the lift curve. We're crossing over that 14 degrees for doing that. And then after that, we're losing, we're going to be, I guess, moving to the right here, which is we'll have a little bit less lift. And so we'll need some more thrust that's coming up there in doing these things. As we continue on down, then we'll get to this point given by the diamond where we're sort of post-stall, if we've got stall, and we're getting a fairly high, more than 30 degrees angle of attack, slipstream angle of attack. So then as we continue on, then we come to this right-hand side here with the asterisk. That's going to put us over at this point on the alpha. So we're coming back in to lower angle of attack, here like around 22 or so. And then as we continue, I guess when you actually have to decrease the velocity because of this fold in the equilibrium manifold. And we can get this other point here. I guess it's pretty close to being back up here at our maximum CL max. So it might be slightly off from that, but just a little bit. And then finally, we can get into conventional flight. So this little section here is conventional flight. This is obviously hover flight. And we see that there's lots of mischief happening in the middle there that could give rise to some difficulties. And we're running across these different situations there. Now, in order to do this, how can we find such curves? Well, we need to use some numerical continuation. And we wanted to do trimming of a couple sorts. We wanted to be able to do an accelerated trim. So we specify the acceleration A bar in the horizontal direction that we want to get. And then we'll trace out the thrust and the tilt angle as we go in terms of the different velocities. So we can trace all of those guys. And the idea here is really based on the implicit function theorem. And so we want to make sure that our Jacobian is onto, and then the null space of that guy will be these tangents here. So we can do all of that. We can solve in this orthogonal direction here. The idea is, we find the tangent. We're going to step out somewhat in that tangent direction. So Z is our tangent, gamma is some step size of how far out we want to go. And then from there, we'll search in the orthogonal space of that guy. And so that's this W that will allow us to search orthogonally there while staying, in this plane station there until we can find the point on the curve that we want. So we can take a look and see how that proceeds when we're doing this continuation to build things up, and then we start to see this funky turns and everything. So if we take this, so here we've got our airspeed is going along this x-axis, our thrust is going along this y-axis, and the z-axis is our wing tilt angle. And we can draw those pictures in a couple of different ways. So we can see here the airspeed and our tilt angle. And it's going to turn out, as we've discovered in the past week, that looking at things in this tilt and airspeed is often a very good thing. Over here, it's very important when we look at the thrust, negative thrust is not going to mean anything useful for us. So when we do that negative thrust, we're gonna have to just cut off this portion of the equilibrium manifold. Now, when we're exploring things, it's okay that we violate sound principles, but anything that we really plan to work with is going to have to obviously not make use of negative thrust. There we go. Okay, so we want to do the transition from conventional flight to hovering flight. So this will be a deceleration trajectory. And how can we go about doing this? So we had a few different ideas. One of them is, can we come up with a good differential equation where we have an input that's showing up? So if I specify U bar and the U dot that I want, then I can solve this guy using F2. I can solve for the thrust and using these two things. So I've got two equations and three unknowns. The implicit function theorem would say that I can, solve for the thrust and the theta W in order to get the acceleration that I want and the zero there, okay? But I can also look at this in a different way. So if I take the second equation, F2, then I could ask, okay, can I make the thrust, satisfying this equation 0 equals F2, can I make the thrust be a function of theta W? Because then I could take that thrust as a function of theta W, put it in the first equation, then I'd have a one-dimensional equation, U dot equals some F of U and theta W. So we did some calculations here. So we want to use the equilibrium curve as a starting point, not a steering point. But if we look at these and we solve the, at different velocities, so each curve here is a different velocity. If we solve for the thrust and the tilt angle on there, then what we see is that I'm always jumping from page to page. Here we can see that the thrust is actually a nice function of the tilt angle, the theta W. So we can get that guy and we can, so here the implicit function theorem gave us these curves. And once we took a look at these curves, we were able to get a graph. So we could think of the thrust. So here T bar is now just a function of the velocity and the tilt angle that we can do. And so we can plug those guys in and get ourselves a nice simpler differential equation, U dot equals F of U and theta W. Again, here's what that guy looked like. So we built up a lot of those things, but now we wanted a way where we could actually integrate this differential equation. So of course, we're not going to find every point there, but what we could do is we could come up with so each of these curves will have its own parameterization because of the continuation method, okay? But what we would like is so we'd have two of those curves. We would like, if we specify the theta W, we'd like to be able to determine what the thrust would be. So the idea with this guy was to do something that we called rails interpolation. So I can think of each of these curves as like rails along a staircase, okay? So here I've got the U1 and here I've got the U2. And what I'm going to do is I will choose the theta W there, and I will interpolate on each of these guys with that theta what the thrust would be. And then I can interpolate in between those. So I can just think of these guys as lines there, and I just put a ski across these rails and do this interpolation. That gives us a pretty smooth surface that we would get for this guy. And so then we can actually consider doing these motions. Okay. So we did some, the royal we, Jake did some nice explorations of these guys. And remember what our differential equation here is we've got the derivative of our forward velocity is equal to a vector field. Here it's just a scalar function, depending on the current velocity and the tilt angle. And the tilt angle here can just be thought to be the input. Okay, so what we did was we said, okay, let's just do open loop integration. Those of you who know me well know that I hate open loop integration, but here are things, you know, when you're working with a one-dimensional differential equation and there's lots of drag, it probably isn't going to go too far wrong. So what Jake did was take our favorite hyperbolic tangent to give us a tilt angle that went from our initial angle for forward flight around 10 degrees. So that ends up being the angle of attack, not in the slipstream, but just in the standard fashion. And then we wanted to let it tilt up until we got up to 90 degrees to see what would happen. And remember our thrust here is such that it will keep us with level flight because we have the W dot is equal to 0. And, you know, so we'll just put this guy in open loop and get what we get for the accelerations. So I guess I should have put this picture a little bit forward. So this is a nice animation that we can hopefully play with here. So we're going forward flight. So we've got our velocity going to there. And so as we go, you know, we've got how long the speed is. So you can see the speed slowing down a little bit. And then we sort of successfully do this job. Okay, so let's look at him. Just the nice thing about the movie is that I can, if I don't lose my cursor, I can actually move this guy along. So here we're going pretty fast. We see the velocity is pretty fast there. We're going 80 feet per second. Our tilt angle 8.6. Then we start to move along the curve. Let's see. Yeah. So over here we can see where we are on this transitioning tilt guy there. So as we move along, okay, so let's go back here at the beginning. So at the beginning, okay, so we've got like 9 degrees in here. So we're actually using up a lot of the lift that's available for this guy. And then as we move along, what we'll see is he's not tilting. How come he's not tilting? Okay, I guess he is. Okay, so as I start to go up on the theta W here, we see that I peak out here at the maximum lift, you know, as I'm coming there, and now I'm going to go over into operating in sort of the stall region. Okay, so we've got a higher angle of attack, both in a real sense, but also in a slipstream sense. So here are, we're up to about 20. So, and our velocity. So we have an interesting thing that happened here. If we look over here at the velocity, this U-bar curve, we see that he's actually going up, so we were decelerating, and then we hit a point where suddenly we're starting to accelerate again. Okay, I guess I don't have a lot of time, so I shouldn't continue. So he accelerates a bit, and then as we continue, then we get sort of back in the natural place. Here we get our sort of maximum angle of attack that's happening, here. So we would expect some buffeting and so on there. And then as we move along, then we trace back up over the lift curve. Now, here, there's something that's really quite interesting. Remember, we've got this angle of attack that's due to the slipstream. And so our lift on the wing is operating perpendicular to that guy, but here that lift is actually what's slowing us down quite a lot. So this is before Jake built up this really nice visualization, that was a little bit hard to see, because normally, since we're moving to the right here with some velocity, we would normally say, that's drag that's doing the job, and the lift would be basically non-existent. In fact, here we can see that our normal angle of attack is going to be something like 70 or 80 degrees, whereas really, with the slipstream, it's down there around 20. So that's a very interesting thing in the part of slowing us down. And then we, just more or less converge to this equilibrium point. So let's just watch that guy again, just so we can see it. Okay, so let's go back and look at this. So we can see a lot of different things happening. So along that trajectory, we're gonna peak up there in this angle of attack. We'll have two crossings there. We're coming down here in our Q bar, and when we get down to something low, then we need to increase it. But we can go forward here, kind of take a look at this maneuver as we go. Now, what is this picture? We can sort of think of this guy as a phase portrait. So we could think of having two states, our U bar and our theta W, and that we can control things making use of theta dot, theta W dot in doing here. And so here we see that, our speed is high here. We're coming down, we're decelerating. We're moving to the wrong slide. So we're decelerating, but then we cross this zero acceleration line. And then we have this small part where we have acceleration. Then we get back on the deceleration side of things. And we'll go ahead and we'll come in and we'll converge to that. So this is actually sort of a nice picture. And what we're largely doing is we're choosing how fast we're moving to the right in terms of this theta. But here we've got this acceleration portion of things. Now, what are these things? The green line here is where our thrust goes to zero. So we're not allowed to be up in this white part. This deceleration is meaning on this side of the dashed line. It just didn't look good in this horizontal liney stuff. And this region on this other side of our zero acceleration curve is where we're accelerating. So we've got that. So here we see that we've got an acceleration there. We might ask the question, can we perform a level transition, decelerating to hover, but without experiencing an acceleration? Well, the answer is no, because if we zoom in on this section there, what we see is that we have to go below this point where our thrust goes to 0, but at that point there is lower in velocity than this point up here. So there's really no way that we can stay in the deceleration portion of things without crossing over. So this picture is actually the big breakthrough of this last week. I think it's one of the coolest things. I think it really can help us inform how we can do some of these things. Now we can try to reduce the amount of acceleration we do by using a higher theta dot. And so starting from this point, here's a bunch of curves where we just use a constant theta dot. And if we let theta dot go to really high speeds, then we would rapidly change our tilt angle and we would hardly have any acceleration at all, because remember, the acceleration period is when we're down under here. Okay, so we got a few other interesting pictures. I think there's not much time. When Jake first showed me this maneuver, we had something here where the acceleration or deceleration went up to something really high there. And that kind of scared us when we were first looking at it, because it looked like, okay, there's something happening there. But here you can see a little bit of the fold that's occurring, and to traverse this thing, with the theta W increasing, we get that extra deceleration that's occurring there. Okay, so we got all kinds of pretty pictures of these things. Concluding remarks, I don't really need to go through those, because I think the most important one is transition is not so easy, and it would be very good to be exploring these things. I will point something out. I had thought for a little while that we could come up with a tilt angle profile so that we could set theta to be a function of the U-bar. Well, the fold doesn't allow us to do that, because we're always gonna hit a point that looks like that. With that, I think I will conclude the talk. Thank you.
All right. Thank you very much, Professor Hauser, for the interesting talk. Such work on that interesting aircraft. I think we have about 4 minutes until the next talk. So I don't know, maybe we can take one question out of the chat, and then the rest will be moving to the Q&A session at the end of this session. So the first question that I see here in the chat is, Professor Hauser, could you elaborate on how to trim at a certain acceleration? Thank you. It is from His-Kwan Chen.
So here, we can look at these two equations. So the equations here are, when we simplified this down, we've got the horizontal acceleration and the vertical acceleration. So here we're setting the vertical acceleration to 0 because we want to be level. Okay, so we've got two equations. We've got 3 unknowns: the velocity, the thrust, and here. So what we know is that if I specify the velocity, I should be able to find the thrust and the tilt angle. But I also know from experience that we can try to trace this guy along. So for example, in this picture, if we set the U-bar dot to be 0, then we can trace out this dashed line that we saw showing up in many of these pictures. Now, it's pretty easy to find some trim conditions. Okay, so we're going fast in conventional flight. We can find that trim condition because we know we'll increase the thrust until we don't do too much. We'll set the angle of attack to be about what we would expect for conventional flight. But then what we can do is we can try to trace this guy out, using that continuation method that we talked about. So I hope that at least in part answered the question.
All right. Thank you very much, Professor Hauser. Again, thank you for giving this talk.
Thank you very much for having me and giving me the chance to talk about this interesting work that Jacob Cook has been working on, and he'll be quickly finishing this. I think this is pretty fun. Okay, take care.